Just a reminder before starting these notes that you do need to read the section before going over these notes. The notes are just a summary. You may not understand the notes if you haven't already read the section. The second day of section 2.2, electron configuration. Talking about atomic orbitals. Within any one energy level, the orbitals have increasing energies. That is, if an energy level has 4 or more sublevels, the S sublevel has the least amount of energy and the F sublevel has the greatest amount of energy. And here's a chart showing the energy levels, the sublevels in that energy level, the maximum number of electrons that can be held in that sublevel, and the maximum number of electrons in the entire level. Remember that 1s has just one orbital, therefore it can hold 2 electrons. 2s, again, the s sublevels only have one orbital, therefore they can hold a maximum of 2 electrons. The 2p sublevel has 3 orbitals. 3 orbitals that can each hold 2 electrons each has a total of 6 electrons. The d sublevel has 5 orbitals, each of which can hold 2 electrons, so it has a maximum number of 10 electrons. And the F sublevel has 7 orbitals, each able to hold 2 electrons. 7 times 2 is 14 total electrons. If we add up all these numbers for each energy level, we can see that the first energy level can hold a maximum of 2 electrons, the second a maximum of 8, and so on. These are 3 rules or principles about how electrons are arranged in varying orbitals or energy levels. The Pauli exclusion principle says each orbital can hold 2 electrons which have opposite spins. The Aufbau principle says electrons are placed into lower energy orbitals first. It's important to note that electrons are represented by single-headed arrows and that the direction of the arrow represents their spin. And Hund's third rule says that electrons within a single sublevel are placed in separate orbitals first with parallel spins before pairing electrons. We'll do some problems that show these 3 rules in action. Here we have the orbital diagram and the chart for filling in electrons. So here you can see that as we go up in increasing energy, we're talking about higher energy levels. But the higher up we go, the closer these energy levels are to each other. You'll even notice that the 3D energy level is just a little bit higher than the 4s energy level. And we're going to talk about what all this means in terms of filling in electrons and energy states of various elements in the periodic table. But the way we start placing these electrons, we could use this orbital diagram and memorize it, or we can use this chart, where we just start writing down all the different sublevels. We write down 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on. Now remember, energy level 1 only has the 1s sublevel. There is no 1p sublevel, so we don't write it down. Similarly, there is no 2d sublevel. It only has 2 sublevels, principal energy level 2. So once you place all these sublevels down, you fill them in from top right to bottom left. So you'll do 1s first, then 2s next, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, and so on until the number of electrons you have for any given atom have been used up, and they're located inside these orbitals or sublevels. Now we're going to do some exercises like the book from page 80, number 17 and 18. Again, we're going to do number 17, but a little bit different. We're going to use bromine instead of the element they use. And for 18, we're going to use oxygen instead of whatever element is in the book. We'll be doing a problem like number 17 from the book. Problem 17 says, apply the orbital diagram method to determine the electron configuration of, and we're going to be doing bromine instead of calcium. This is the orbital diagram method. We're going to start placing electrons in. We place one in the 1s and then an opposite one with the opposite spin. 2s, 2p, Actually, before I keep going, I need to know how many electrons I need to put in. That's the periodic table's for. Bromine has a total of 35 electrons. So I need to put in 35 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm at 10 electrons right now. 11, 12, 13, 14, 15, 16, 17, 18. 4s has the next highest energy. 19, 20, 21, 22, 23, 24, 25. And again, we place one electron in each orbital with parallel spins first. 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. That's the electron configuration of bromine using the orbital diagram method. 18 from the book, except we're going to use the element oxygen instead of the element they use in the book. The question asks us, deduce the number of unpaired electrons present in the oxygen atom. So we need to write its electron configuration. One s gets filled in first, and it can hold a maximum of 2 electrons. 2s gets filled in next, it can hold a maximum of 2 electrons. 2p gets filled in next, and we only have, how many electrons are there in oxygen? Its atomic number is 8. It's an atom, not an ion, so it also has 8 electrons. 1, 2, 3, 4. P can hold up to 6, but we only have 4 more electrons left over. So for this sublevel, we have 3 orbitals with 4 electrons. We can see that 2 of them are unpaired. This is just some interesting math that has to deal with sublevels, orbitals, and electrons. The number of sublevels in any main energy level is n. So the principal energy level 1 has 1 sublevel, energy level 2 has 2 sublevels, and so on. The number of orbitals in any energy level is that energy level squared. So for example, in principal energy level 2, we have a 2s sublevel and a 2p sublevel. 2s has 1 orbital. 2p has 3 orbitals. 1 plus 3 is 4. There's a total of 4 orbitals. 2 squared is 4. Similarly, energy level 3 has 9 orbitals. 1s, 3p, and 5d. When added together give you 9. And the number of electrons is the number of orbitals times 2. And this should be the maximum. The maximum number of electrons is 2 times the energy level squared for that energy level. It's the number of electrons that energy level can hold. And we're not going to talk about the quantum letter L. So as I mentioned before, the 4s and 3d sublevels are very similar in energy. And in the order in which we fill the sublevels, 4s is filled up before 3d. However, once there are electrons in the 3d sublevel, it pushes the electrons in the 4s sublevel to a higher energy. So when the d block elements react, they lose their 4s electrons first. Now we're going to do a few examples from page 81. And then we're going to state the full electron configuration for nickel and state the number of unpaired electrons it has. We're going to do a problem like the worked example from the book. We're going to be using the element nickel instead of the one they're using in the book. This problem is found on page 180. It says state the full electron configuration and deduce the number of unpaired electrons. So step 1 is look up how many electrons nickel has. Nickel is located here. It has 28 electrons. We start filling them in based on this chart we can make. And that's probably enough. We start in the top right-hand corner and work our way down. 1s. The s sublevel can contain a maximum of 2 electrons. 2s comes next. Again, a maximum of 2 electrons. 2p, then 3s. 2p, a maximum of 6. 3s, a maximum of 2. And I'm running out of space. I'll just continue it down here. After 3s comes 3p. 3p can hold a maximum of 6. Let's see how many electrons we're at so far. 10, 18. All right, keep going. Next is 4s. Can hold 2. Next comes 3d. We're now at 20 electrons. D can hold a maximum of 10. We have currently 20 in our suborbitals. Our sublevels, excuse me, which means we have 8 electrons left. We'll put those 8 there. If this were 9 or 4, we would borrow 1 from here. And also note that since we're now putting electrons in the 3D sublevel, the 4s energy level is actually higher than that of the 3D. So we could actually more accurately write this this way, this being the full electron configuration for nickel. And the second part of the question is how many unpaired electrons are there? We have to go to this empty sublevel, or not empty sublevel, not completely full sublevel. 1, 2, 3, 4, 5, 6, 7, 8. There are 2 electrons unpaired. 2 unpaired electrons. We can also use an abbreviated electron configuration. The electrons that react are the ones in the outermost shell, or they are the outermost electrons. So it's sometimes convenient to write the electron configuration ignoring the inner electrons that don't react. The way we write the abbreviated configuration is we take the noble gas from the previous row and put it in brackets, and then we finish the electron configuration as normal. These are some period 4 elements. They're in the 4th row. And so the noble gas in row 3, the one before it, is argon. So we can just say the electron configuration of titanium is the same as argon. The inner electrons are the same as argon, but then it also has 2 3d electrons and 2 4s electrons. And again, we write the 3d electrons before the 4s, even though the 4s fill in first, because once we start filling in 3d electrons, the 4s electrons are pushed to a higher energy state. The electrons in the outer energy level are mainly responsible for compound formation or bonding, and those are called valence electrons. Lithium, for example, has 3 electrons, but only one of those electrons is in the outermost level. This is the electron configuration for lithium. And the outermost electrons in the 2s sublevel, there's just 1. Phosphorus has 5 valence electrons. In principal energy level 3, we have 2 electrons in the s sublevel and 3 electrons in the p sublevel. These are its valence electrons. I'd like to point out that the number of valence electrons has to deal with what columns the elements are in. And we'll learn more about that later on in, I think, the next chapter, or maybe chapter 4. D block elements. The 3D sublevel is written below the 4s sublevel when used, even though the 4s electrons were filled in first. And I've mentioned that already. But what I haven't mentioned is chromium and copper have unusual electron configurations. For example, you'll see that the electron configuration of chromium is that of argon. Then it has 5 3d electrons and only 1 4s. Similarly, copper has 10 3d electrons and only 1 in the 4s sublevel, when normally the 4s sublevel is filled in first, 2 electrons, and then the 3d sublevel is filled in. And the reason they have these electron configurations is due to increased stability from half full or fully full sublevels. So chromium would normally have, or you would think it would have, an electron configuration of 4s2, 3d4. But if we move 1 electron from the 4s to the 3D so that its electron configuration is as shown, the 3D sublevel is now half full, and there is a stability from that. Similarly, if we move one electron from the 4s, normally you would think copper would have an electron configuration of 3D9, 4s2, but if we move one electron from the 4s to the 3D, which is as shown, the D sublevel is now full, and therefore it has increased stability because of that. We're going to talk about the electron configuration of ions. The way we do the electron configuration of ions is a little bit different for anions and cations. Anions is simpler. If we're doing the electron configuration of an anion, we simply add the extra electrons into the next available sublevel. So here's the electron configuration for sulfur. 3p4 are the last electrons that are put into the sulfur atom. The sulfur ion has a charge of -2, so it has 2 extra electrons. Those 2 extra electrons just go into the last sublevel. With a cation, it's a little more complicated. We first write the electron configuration of the atom, and then we remove the highest energy electrons first. And that's important because for the case of D block electrons, like chromium for example, the electron configuration of chromium is as shown here, 3d5, 4s1. But the chromium 3+ ion says, okay, you have to remove 3 electrons to have this +3 charge. The first electron that gets removed is the 4s, because once we start filling in the 3d, the 4s has a higher energy level than d. So first we remove the 4s electron, and then we remove 2 of the 3d electrons. So the chromium ion has this electron configuration. Here's the electron configuration for cesium. I just want to show how the electron configuration has something to do with where the element is located in the periodic table. Cesium is located over here. Its electron configuration is 6s1. Notice that the highest energy level 6 corresponds to what row it's in. And the number of valence electrons it has, 1, has something to do with what column it's in. So based on the electron configuration, we can find out where the atom is located, or vice versa. If we know where the atom is located, we can predict its electron configuration. Same thing with iodine. Iodine is located right here. Its electron configuration is that of the noble gas in the row before it, and after that it has 5s, row 5, these 2 electrons, 4d, these d block, and then 5p, and then only 5 more electrons. And that has something to do with the column it's in as well. The 7th or 17th column shows that it has 7 valence electrons, 5 in the 5p sublevel and 2 in the 5s sublevel.